Understanding collision rates is important for our understanding of kinetic parameters regarding chemical reactions. And so to kind of break this down, I have figure 1.11 and 1.12, and I'm going to relate this to our collision rate equation, which is right here. And so I'm going to assume that R1 and R2 are the radius of our fixed molecules, molecule 1 and molecule 2. And when we combine these, we get B max, which is the combined radius right here. And so another variable we have is B, which is the perpendicular path of incoming molecule 2, which is right here. And so a collision will occur if B is less than B max, and no collision will occur if B is greater than B max. This is because when B is less than B max right here, the surfaces of these two molecules will overlap, meaning a collision will occur. If this B right here is really big, the surfaces won't even touch, meaning no collision will occur. Next, I'm going to bring this surface area section and we're going to relate it to a volume. So basically what I can do, since we know that B max is the combined radius of both molecules from center to center, we can act as though this is the radius of this circle right here. And so we know that pi r squared is the area of a circle. And so B max squared is our radius. So now that we have area, we can also find the length of this cylinder. And so we have the relative velocity of this molecule right here is equal to meters per second. We also have the change in time, which is equal to seconds. And when we multiply these two, we have meters per second times second. We can cross out these seconds and we're left with meters, meaning that relative velocity multiplied by change in time is equal to our length. And so we know that when we're given an area and we're given a length, we can multiply these two to get a volume. So when we have these volumes or these values, we can find the volume of the cylinder. So given the cylindrical volume, now we can find how many molecules are in the volume. And so we know that any molecule that has a center from here or closer is going to collide with this molecule. So what we can do is we can take N2, which I'm going to say is the density, or the molecules per volume times volume. And when we do that, we can take our volume right here, we can multiply that, and then our volumes will cancel out and we're left with molecules. And so we know that N2 times this volume is going to give us the number of molecules in that cylinder. So now what we can do is we know that any molecule in that cylinder is going to have a collision. And so we can take our N2 pi b squared max times the relative velocity, and then we can take our time, divide each side by t, and with the assumption that b is less than b max, we can turn this into collisions per second. So now we have our collisions per second, which is our collision rate, or Z2. And so that is how this equation right here can relate to these two figures.